I'm running out of space on my desktop. I need to do something here. Let's see, which one of these is the first one? This looks second.
I think that's the second one.
Yeah, this is going to be the first one. Tell me where you want to start.
Just with the first one, because I haven't really looked at this.
So it looks like we're doing similar polygons. So let's talk about similarity compared to congruency for a moment. These two triangles are congruent as long as they satisfy one of the postulates. In other words, as long as they are side, angle, side, or side, 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 or one of those. In other words, it means they have the same length sides and the same angles. That's what makes them congruent. But if I draw a triangle that's just the same three angles, and that's got the same three angles as this one, then those two triangles are similar. Okay?
Yeah.
Similarity has lots of interesting things. The most important is that the ratios between corresponding parts are the same. In other words, if that's angle 1, angle 2, and angle 3, and it's the same as that angle 1, angle 2, and angle 3, then I can say that 5 is to 10, as 6 is to 12, as 7 is to 14. Okay? So you can say that the ratio of corresponding parts is always the same as long as triangles are similar. But there's even a further ratio proportion that's equal. Even if I look at the ratios within that triangle, let's say 5 is to 7, well, that's the same as that ratio is to that ratio. That's the same as 10 is to 14. So it's not just that the ratios are the same between corresponding parts of the triangles, but all of the internal ratios are the same also. Okay? So all of these problems that we're going to look at here are going to have to deal with ratios. Problem 1 has to do with this triangle and this triangle. Says that they're similar.
All right.
And the area of the bigger one is 72. What are we asking for? R sub L. What is R?
That just stands for ratio, right?
It's number 6 or 8?
6.
Okay. So what's the similarity ratio between these two triangles? That's always the first thing you need.
That's a 2-to-1 ratio, or 1-to-2.
Exactly, depending on whether you're talking bigger to smaller or smaller to bigger. I always like going bigger to smaller because I prefer to deal with ratios that are greater than 1, not less than 1. So the first thing I notice is my similarity ratio is 2 to 1. Okay? Now, that does not mean that my area ratio is 2 to 1. Your area ratio is always the square of the similarity ratio. So the area ratio is going to be 2 squared to 1 squared, or 4 to 1. So the area of this bigger triangle is 4 times the area of that triangle.
Okay.
So what must the area of this triangle be?
Whatever 72 is divided by 4.
18. 18.
Yeah.
Okay. And so I'm still not sure what R sub L means. You know? In other words, we answered this, but I'm not sure what they mean by R sub L. Do they mean that means the linear ratio. Okay, the linear ratio is 2 to 1. And R sub A means the area ratio. And that's 4 to 1.
All right.
Okay. And let's go over that a little bit, because this is an extremely important part of math. Let's take a square. It has a dimension of 2 by 2. And another square that has a dimension of 6 by 6. What's the similarity ratio? Or what they would call R sub L. What they're calling R sub L means the linear ratio.
Okay.
What is it here?
1 to 3.
On this diagram here that I've drawn.
Yeah.
What's the linear ratio?
I'm not sure.
6 to 2.
Oh.
Linear meaning one side only, one line.
Okay.
Okay. So the linear ratio is 3 to 1. What's the area ratio? Take the linear ratio and square it.
9.
9 to 1. Now, let's look at a cube. That has dimensions 6 by 6 by 6. Now we actually have something called a volume ratio. What is the volume of that relative to that? Well, it's the linear ratio cubed, not squared, but cubed. 27 to 1.
Okay.
Okay? So these 3 ratios are always this way, whether you're talking triangles, squares, rectangles, circles, anything where you can go from 1 dimension to 3 dimensions. Notice here, I'm measuring stuff in inches, okay? That's 2 inches. Well, when I'm measuring area, I'm measuring it with square inches. And when I'm measuring volume, I'm measuring it with cubic inches. So that lets you know whether you're linear, area, or volume.
Okay.
Now, so let's do a simple one here where I have a circle whose radius is 2. And I have another circle. All circles are similar by definition, whose radius is 5. So what is my linear ratio?
2 to 5.
Yeah, or 5 to 2 if you always want to keep it as a number. In other words, like I said, either answer is correct, but I think it pays to always take big to small.
All right.
Okay. What is the area ratio?
How do you square 5 to 2?
Square 5 halves. Square the numerator and the denominator.
Oh, 25 over 4.
Right. Notice that's almost 6 to 1. This was only 2.5 to 1. So the area of this circle, even though the radius is only 5 to 2, the area is like more than 6 times this area. And if I had a sphere, which I'm not going to be very good at drawing, but let's say I had a sphere that had a radius of 5 inches, what is the volume ratio going to be? 5 cubed over 2 cubed.
125 over 6.
Over 8.
8.
That is like 15 to 1. Okay? It's why giants are impossible. In other words, there is a maximum size creature that can live off this planet. And it's entirely based on this reasoning. Is that if I take a creature who has a radius of 2 inches, and I keep increasing its size, even though I may only double its size, I triple its volume.
Okay.
If I go from 2 inches to 10 inches, I've increased the linear ratio by a factor of 5, but I've increased the volume by 125. And
all right.
They don't have big enough legs to support that kind of weight. So it's hard to have giant things on planet Earth. And it's because of this fact that volume is the cube of linear. Whatever the linear ratio is, the volume is going to be the cube of that ratio. Just like area is the square of the linear ratio.
All right.
Now let's... Rectangles, the same thing. Any polygons that are similar. And similarity here means not only do I need all 4 angles to be 90 degrees in both figures, but I need these ratios to be the same. Okay? They're giving you the area ratio. The area of the rectangle versus the area of whatever that says there. I think that's the other half of angle, rectangle.
Yeah.
I think that's a typo. But what they're saying is the area of this rectangle is 9, the area of this rectangle is 16.
Okay.
So, what's my area? That's my area ratio. That would be R sub A, 9 to 16.
Okay.
What's my linear ratio?
Is that just the same ratio squared?
Square root of.
Okay.
Notice they didn't start off by giving me the linear ratio.
Okay.
They gave
so
me
that would.
They gave me the area ratio. So if I want the linear ratio, I've got to take the square root of this. And the square root of that is 3 to 4.
Okay.
Okay? So
yeah.
This side right here has to be 3/4 of this side. And that letter must be T, correct?
Yeah.
So this answer, TR, has to be 18. Because TR relative to whatever this side is has to be in the ratio of 3 to 4. So the area ratio is 9 to 16. The linear ratio is 3 to 4. Ah.
Okay.
And what is R sub, what is that letter right there?
V for volume.
For volume, that's a V. Oh, yeah, okay, that's what it should be. So how am I going to get the volume ratio?
You square the area ratio.
No, not quite. You square the linear ratio to get the area ratio, but you cube
the linear
the
ratio.
linear to get the volume. In other words, it's hard to go from area ratio directly to volume ratio. You kind of have to go backwards and get the linear ratio and then cube it. So if the linear ratio is 3 to 4, what's my volume ratio?
27 to
64.
Yeah.
And notice that's less than half. So I have a linear ratio that's 3 to 4. That's 75%. But by the time I've turned it into a volume, once I get a volume rectangular brick, the smaller brick is less than half of the volume of the larger brick. And that's the way these always go.
Okay.
How many do we have here? Just 4?
Yeah. On this, well,
This was the first
7.
page. Okay. Well, let's see. We have another session this week. I assume we'll still be on this stuff. Maybe, maybe not. This is going to go pretty quick. Once you get the hang of it, it's the same for all figures. It's not different for trapezoids than rectangles or circles or squares, as long as I have similar polygons.
All right.
Okay?
Can we work on number 7 then?
Yeah. I'll have to go to the other page.
I think it's just lower on. Yeah, it's on the other side. Well, it's just lower on the same page.
Yeah, there it is. The lengths of the edges of two cubes are in the ratio of m to n. So there's one cube, has an m, and there's another cube, we'll make it bigger, and it has a side of n. So there's the ratio. That means the linear ratio is m over n. I don't really care which one's smaller. What is the ratio of their surface areas? Now, as it turns out, surface area is the same as area. So, what's the ratio of their, in other words, the ratio of their surface areas is going to be the same as the ratio of their area.
Okay.
Whether it's surface area or just the area of an individual face, it doesn't matter. So what's the ratio of my surface area going to be?
That's just going to be, it doesn't, it's just m squared over n squared.
Exactly.
Right?
In other words, you do the same thing as you would do if you're going from linear to area. Surface area does not change it. Surface area is, and the way you know that is that surface area is 2 dimensions. When you're measuring surface area, you're coming up with square inches. You're not coming up with cubic inches. And you're not coming up with inches. You're coming up with square inches. In other words, surface area is very similar to area. The way we get the surface area of the cube is we take the area of each face and we just add all 6 of them together. So area and surface area are virtually identical for the purposes of these problems. We don't have much time here. Is there any question that you
I think that's it. I think we're good on that. Oh, this sheet.
Now, yeah, some of these, in other words, they give you the volume and they give you the surface area. And so you kind of have to take the cube root of the volume ratio to get the linear ratio. And then you square the linear ratio to get the surface area ratio. Okay, so they're not always going to make it simple. They're not always going to start off by giving you the linear ratio and asking for the other two. They might give you the volume ratio. But usually what you have to do is come up with the linear ratio at some point in time. And once you get the linear ratio, then you can come up with the area ratio by squaring it or the volume ratio by cubing it.
Okay.
All right, Mark. I will talk to you on Thursday.
Yep.
Okay? All right.
Thanks, David.
Talk to you in a couple of days. Bye-bye.